All right, so for the next couple of slides, this is what we're going to be talking about. We're going to be doing stoichiometric calculations, so we're going to be working on our mole concept, both on the macroscopic and microscopic level, and to do stoichiometry calculations, including limiting reactants. So this is figuring out that if I have, for example, 30 grams of H2S, 50 grams of oxygen, how much S8 am I going to make? And by the time you're done with the next 2, maybe 3 videos, you will have an answer to that question. Now that we've got the basic intro for stoichiometry out of the way, let's talk about the full process. So here's a roadmap of what we're going to be doing this time. This is a figure from your textbook. And we're going to be focusing on this pathway right here that relates the mass of one reaction component to the mass of another. Now remember, the idea is that chemically it's moles that are the relevant factor because things react mole to mole. And that's what the coefficients in the equation tell you. So that's what the stoichiometric factor is. But we can't measure moles directly, but we can weigh stuff real easy. So we need a link between something's mass and something's amount, and that is the molar mass that we developed a couple lessons ago, which is a link between the two. So this is kind of the general path. You start with the mass of one component, convert it to a number of moles using its molar mass. Using the coefficients in the equation, you can turn that into an amount of the other reaction component. And then finally, using the molar mass of B, you can get its mass. So when we're doing this step by step, we're actually going to start here, which is a review of the last video, and then do the full-on mass to mass example. So I'm going to stick with the reaction that I used in the intro video, the reaction of H2 gas with N2 gas to form NH3, which is ammonia. So look at the coefficients in the equation. So the idea is that if I have 4 moles of N2, and let's assume you've got plenty of H2, how much NH3 will you make? Hopefully you can look at the reactions and say, well, they react 1 to 2, so I should make 8 moles. Let's talk about the full process for that, how to set up the problem so you can set up any other problem where the numbers aren't quite so easy. And think about this in terms of this whole starting point, conversion factor, answer thing. And in this case, the conversion factor you construct from the coefficients in the equation. And this tells you that sort of that 2 moles of NH3 is equivalent or equal to 1 mole of ammonia, or I'm sorry, 1 mole of N2. And whether you use 2 moles of NH3 over 1 mole of N2 or the other way around, the units will tell you. Your answer needs to be in moles of NH3. So this is the version of the conversion factor that you want to use. And as the way that you can prove this to yourself is that in this case, moles of N2 cancel. And so we've got 8 moles, and I would encourage you to, at this point, start writing the species so you can keep track of what's what. So we have 8 moles of ammonia expected to form. So let me give you another example, give you some more practice, and point out another fact. So what if we had that same 4 moles of N2? Then the question is, how much H2 would you need to react along with it? How much would that consume? That's the word chemists like to use. And this idea of using the conversion factor built on the coefficients in the balanced equation, it doesn't matter whether it's a reactant and a product, 2 products, 2 reactants, the process is the same. So we're going to start with 4 moles of ammonia. Now what's different here is that we now have this conversion factor is now 3 moles of H2 over 1 mole of N2. And again, we're convinced that this is the right setup because the moles of N2 cancel in this case, giving us moles of hydrogen. And work out the numbers, and that gives us 12 moles of H2. Okay, so this is kind of what we did before. Hopefully it's starting to make a little more sense with the repetition. Now let's increase the complexity just a little bit. So what if I gave you a starting mass of N2? Now this is a different quantity of N2 than the previous example. But if I started with 100 grams of N2, how many moles of NH3 would I expect to make? And so there is just one addition to this. You need to convert this amount of N2 to a mass. I'm sorry, this mass of N2 to an amount. And the molar mass is a way to do that. So I've got the 100 grams of N2, and now what we're doing here is we're multiplying, or actually dividing, by the molar mass. And you can tell the direction you need to do, you can tell from the units. So you want grams of N2 to cancel, giving you an amount of N2. And then finally, the coefficients in the equation will tell you what the amount of NH3 is. And so let's talk about what each of these steps is doing here. So if I did just this, that gives me the amount of N2. And then the last step just gives you the amount of NH3. So let's check our units. So grams of N2 cancel. Moles of N2 are going to cancel, giving us moles of NH3, which is what we wanted. And if you just punch the numbers through and keep it to 3 sig figs, that's going to make 7.14 moles of ammonia. So I'll let you do one. Take that same 100 grams and tell me what amount of H2 I'm going to need to react with that. All right, so same deal here. And I've got the 100 grams. So the mass of N2 cancels. The amount of N2 cancels. I'm left with an amount of hydrogen, which is what I wanted. And that's going to be 10.17 moles. So here's the last level of complexity, which is relating the mass of one component. That should be a G here, to the mass of the other component. And this is just one step added on to the end. And that's going to be this one right here, which is the molar mass of the second component, in this case the ammonia. So I've got my 100 grams. So at this point, this operation here up to this point would give me an amount of N2. The operation up to this point would give me the amount of NH3, and then after here, this one will give me the mass of the NH3. And let's walk through that with the units. So here, this cancels out the mass of the N2. The amount of the N2 cancels out. And finally, the amount of the ammonia cancels out, giving us a mass of NH3, which is kind of what we wanted. And then you can just punch the numbers through, and that should give you 122 grams of NH3 that will be produced. And give you one to try for yourself. Same deal, 100 grams. What mass in grams of H2 do you expect to be consumed? So the setup is pretty comparable. You've just got, again, the molar mass of N2, the coefficients in the equation, and then the molar mass of H2. Do the dimensional analysis. Grams of N2 cancel, moles of N2 cancel, moles of H2 cancel, giving us a mass of H2, which is exactly what we wanted. And that gives us, that's going to mean that we're going to need at least 21.6 grams of H2 to react completely with that N2. A couple of things to note. Keep track of, or be mindful of the molar masses and make sure it's the molar mass for the right component. That's a pretty common mistake that I see. And the other thing is that, check to make sure that the equation's balanced. So these coefficients here are the conversion factor between one component and another. So it's important that you get them right, which is why we, led you through the exercises of how to balance equations. So check. And so that's about it. The setup is pretty much going to be the same. And the other thing that, remember, always, 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 things react mole to mole. So whenever you are relating some quantity, whether it's amount or mass, of two components in a reaction, somewhere you have to have a factor like this that relates them mole to mole based on their coefficients. Now, depending on exactly what I'm asking, you might have these molar mass steps as well, but this has got to be in there somewhere. So make sure about that. Things don't react gram to gram, they react mole to mole.